If everybody is ready, we can start. We are keeping on with Mr. Kashif Yaqub again about electron gun principles.
Thank you very much. Just recall that I was asking about the circuitry that is required for the operation of electron. The same concept applies to any source, be it a plasma source or electron sources. I have drawn a little cartoon. I always draw this just to give my students a flavor of how something can be accelerated. It's just a common play site. If I don't know how to call it in Turkish, but maybe you call it slide or whatever. Children, they usually gain a potential energy at a certain height, and then they are released from a higher potential, and then they enjoy. It's a very common sight. In fact, we have to do the same for plasma sources, for electron sources. Let me show you why. Consider that we have a source, a dispenser cathode, and you have heated up and enough electrons are coming out. You have now the focusing cathode and you have anode. Okay? In principle, what you do is that you connect your heater with a low voltage power supply. Usually it's up to 7 volts or 8 volts, depending upon the heater. Okay? And it is supplied with AC voltages usually. DC is also done, but let's talk about AC for the moment.
Is there a difference between them?
I'm sorry?
For the purpose of heating.
Yes, for the purpose.
Is there a difference between AC and DC?
Yes, there is a little difference. It's a minor difference. Let me finish with it. We'll talk. Okay. And then we have to apply the accelerating voltage, very high negative voltage between the cathode and the anode. I draw equivalent potential curve. The electrons that are emitted have few EVs of energy because they are called thermal electrons. Thermal electrons. If this is the distance d and this is the potential, you see that this is around minus 30 kV or something. So the EVs, few EVs is just like nearly zero potential. And they have to cross this negative barrier in order to get through this sort of potential. I'm drawing the magnitude. This is minus 30 kV magnitude, and anode is held at 0. So this is the problem, physical problem that electron face right after they are generated. They are at the bottom, maybe perhaps the sub-level of the potentials when they are generated. In fact, a child which is sitting or standing at the ground, we have to shift the child to the top of that swing, that slide, and then the velocity can be gained. We do the same. Another problem. This negative potential will in fact suppress any electron that will try to come out. There will be no emission at all. And second thing, which is worst, this is at 7 volts. This electrode is at minus 30 or minus 50 kV. Suddenly there is going to be a spark. Maybe I can draw the red line. Disaster. It will burn. So it's not going to work this way. We have to devise a scheme. Maybe it's too rushy, I will draw a new diagram. Or I can use a different color maybe. Okay. So what you do is that you take your electrons and shift them on the top of these potentials. How do we do it? We raise the ground of this supply to negative 30 keVs. Of course, in electrical engineering terms, the potentials are, in fact, with respect to a certain reference. Okay, we have this around maybe 220 volts. They are with respect to the ground. So what if the ground itself is at minus 30 kV? On top of that, you are adding 7 volts. So it's a very famous phrase that LV rides on top of HV. What happens now is that we have shifted, this is the potential. We shift our electrons from ground or any charge to this level just by connecting the low voltage power supply, the ground of low voltage power supply to minus 30 kV or the whatever voltage you want.
May I ask you,
Sir,
why don't we are increasing the potential of the anode rather than the cathode decreasing?
a very nice question. It is the human interface. Anode is usually the part where experimentation or all the things are gone. So you can this part is always held at ground. It has to be. So because
Case of instrument.
it's a case of instrument, yes. So whatever you can do, that's why we need high insulation. Someone was asking about why you need ceramic insulation. That's why the insulation, the magic of insulation come. Okay, so far I guess it's clear, but this gives us another problem. You cannot short the ground with this 30 kV right away. So let's see. I again draw this thing. The low voltage supply of the cathode is fed through an isolation transformer. A transformer that provides the isolation between primary and secondary of way greater than the HV that is being applied at cathode and is shortened with this thing. Only then the ground of the lab doesn't know at which level the low voltage power supply is working. This concept is subtle. It's not easily understood, but those, I'm sure, the people who are operating plasma sources or electron guns, they must be using this scheme. I personally don't see any gun that is not operated this way. In klystrons, let me use this opportunity. You have a big tank, you have an isolation transformer built inside, and the electron gun is dipped in the water, in the oil tank. This oil is providing the isolation, of course, and the supply, which is LV plus HV, is supplied through a step down plus isolation transformer. And then you can easily connect the primary to your usually 220 volts single phase or 3-phase power supplies. In terms of graph, let me put it here again. The electrons are basically on top of that thing, the potentials, the very little potential of the electron power supply or the plasma power supply is actually on top of this HV power supply. That is the mechanism of it. Let me go through it again. The problem was that the electron that come out of the cathode, they are of a very thermal low energies. They need to get on top of the HV before they are released to gain the velocity due to the potential. This cartoon is perfect to understand this is concept. First, you have to raise your mass to a certain level and then release it. The potential is converted into the kinetic energy. Here again, the electrons go to very high potential, but remember this phrase, always remember this phrase, LV rides on top of HV. And how do you do it in practice? You just connect the ground of the low voltage power supply with one end of this thing.
Sorry.
If this is, just a second. If I'm not sure if it's working.
Working, but
And then
you can, I think, two microphones are interfering. Move to your mouth. No.
go close it.
Just close it.
Hello?
Yes.
No, you hear me? Maybe it's a bit weak now.
Yok. Temas değil, mikrofon uzakta kaldığı için bir ses dönüp bu şekilde şimdi yer başka bir şey.
Should it be okay?
Is it
No?
okay? No?
It should be okay now. It should be okay now.
Maybe
It's directional.
we can open this one.
So, okay. So I was talking about the configuration in which the electrical configuration in which electron guns are operated. So you have to short your low voltage power supply. You have to raise the ground of your low voltage power supply to the same level of the potential that is applied between cathode and anode. Only that way you can preserve the arcing. Only this way you preserve the suppression of the electrons. Okay, I'm sorry about the transmissions of voice, but I didn't realize that you guys couldn't hear it. Okay, is this concept clear? If nothing is, if something is missing, we can discuss it later. But the key is that the operation of electron gun demands high voltage handling plus low voltage handling. Once you have set your low voltage, you cannot really go to the controls and manually change it. You have to do it with remote handling.
Kashif, come back to the second slide. Yeah, this one. Now you are using the isolation transformer.
Yes.
And also you are connecting the secondary with the minus 30 kilovolt.
Yes.
Does not affect the working of the secondary? Because it's very high voltage, 30,000 kilometers.
Yes, it doesn't work. It doesn't actually interfere because this is DC and this is AC, and even these in the pulse format, the frequency of the transformer usually is held at 50 hertz or something, so it's not going to affect it. It doesn't affect because this voltage level is very, very, very low as compared to this DC. The actual magic comes from the isolation of the transformer. You were let me draw a bit of the isolation transformer. What it is actually. You have this core. This is the primary, and the secondary is bound away from the core, and this portion is either filled with oil or very high polymer, which provides it additional isolation. So you were asking about the AC operation and the DC operation of the cathode, the low voltage DC power. Imagine that you have a cathode that has its cathode attached to a DC source. This is working. This is acceptable. But with the passage of time, this acts as what you call once they have their own oxidation and etching effect. One leg gets weaker as compared to the other one. It's just like the electrodes dip in a solution. The electrolysis sort of chemistry happens. So one leg gets weaker and weaker and eventually breaks. That's why people prefer to operate their cathode in using AC operation, AC supply. In that case, the polarity of the two legs is quickly shifting, and there is no oxidation taking place, or no reduction is taking place. Reduction and oxidation in chemistry terms. Okay, so that's why the DC operation is okay, but AC is preferred. Okay, so I quickly go to my presentation, and I try to finish on time. Thank you. So, okay. Are you able to hear me? No? I think the battery of this device is weaker now. Maybe you need to change it. If you have another microphone, I can. This one, yeah. Thank you. The pointer. So quickly moving on. So this scheme. So this scheme is now obvious to us. Why we have this thing? The 10:1 is basically to provide a good resolution for the supply. But the isolation principle is now clear to us, and why we have shortened it, it's now clear. Let's go to the lab. This is from done. Few electrodes. Now the pulses are taking up. We are catching up the. This is the pulse operation. Sorry, you're making pulse. Let's finish this thing. These are the solid line power supplies and the corrector power supplies, which are used to drift it. No, it's a pulse power supply, a solid state pulse power supply, which is generating a variable pulse width. For example, here you have around 4 microseconds. This is the yellow pulse is the voltage pulse, and the bluish pulse is the current pulse that is coming out. So it's a power supply made by Scandinova. There was a software screen, so we bought it from them. We are also developing our own pulse power supplies, but this particular setup was operated by this thing. Okay, so our characterization, it remains to be handled. We need to know the state vector, meaning thereby we need to know the slope, we need to know the emittance, we need to know the twist parameters. By the way, these guys have name called twists. So what we do, we change magnetic strength and we keep an eye on this beam spot. A moment will come when the beam will be very focused, and when we and in fact, if I keep on increasing the strength of my magnet, the beam will again start to defocus.
Why?
Why? Yes, excellent question. We have a screen, just like the screen. At the end of the screen, because I am changing the strength of my magnet. If it is a certain strength, it is focusing here, and after that focusing point, the beam is diverging. If I increase the strength of my magnet, the focus point will shift. Focal point will shift. So that's why the focal length is changed, and I have a sort of this graph.
It's ready.
So this technique is used to evaluate the emittance of the gun, because we knew from our yesterday's lecture that emittance is basically when the shadow of the emittance ellipse is the footprint of your beam. So if you know the footprint of your beam, that is the image of the beam, you can always back calculate using matrix mechanics, the transverse thing, the transfer matrix things which I discussed yesterday, to evaluate the twist parameters of the beam. This sigma are basically the beam sizes, the sigma, the beam spot size. The B is the strength. So there's a mathematics. The beam is here. This is the beam spot. It is little bit what you call aberrated, because the magnet was not finely aligned. But if you can manage to manage this, to have a size of it, that's why we had a camera installed at the end of the beam line. So you have to measure the beam size in X direction and in the Y direction. Then you will do some mathematics. I have a book at the reference. I have no time to go into the detail of the emittance measurement, but it's another 1 hour lecture, so I don't want to bore you anymore. Anyways, so the thing is that by changing the strength of the magnet and by looking at the corresponding image sizes, we can evaluate the twist parameter. For example, I'm changing the magnetic strength and I am checking where the minima and then again maxima occurs. If you can think of it as a part of the ellipse, this blue line is the experimental line and the red line is the polynomial fit. We do some post-processing in MATLAB. So basically, this thing is the part of the equation, the Hill's equation, the equation which we used to draw the ellipse. So we know the part. If the part of the ellipse is here, we can guess what the rest would look like. Okay. So this is emittance measurement is the first job of any accelerator operator at the start of the day. First, we should know the parameters. So alpha, beta, gamma are evaluated, and then the emittance is measured. In that way, we check that what is the actual performance of the gun that has been made, and then we try to compare it with the theory. There are different experiments, but the message is clear that we do the measurements, and then we check. Well, this is, for example, in emittance wise, it was giving us rather better values sometimes, and we wondered what we have invented, but yeah, it's closer, not very different. Okay, I hope that we can play some game now. I present to you some accidents, and I want you to be the investigators. Let you investigate what went wrong with our system. Okay. Can you concentrate on this picture? And you can see a leg broken, melted. This was an accident that took place about 3 weeks back. Yeah. And another accident. This was a filament leg melted accident. This was another event with a very different gun. Here, the insulation, the ceramic got shortened with the flange. The coir was compromised. The insulation was compromised. Remember that we have to apply the potentials. Here, the potentials are around 30 kV. So the investigation has begun. Only when you are able to investigate your problem, then you keep on improving. And you are free to do investigation once you have made things yourselves. Only then you know the physics behind the drawbacks. Well, I know what I am, so I can either spoil myself or I can make myself better. Huh? So what do you think? What could have happened here? Maybe take it as an homework.
Spot welding. Oxygen there.
Not a good vacuum. One, spot welding. The other, you have to give reason.
Because of the oxygen.
Because of the oxygen. The vacuum was quite good. Let me answer. Investigate me. You are the judges. The vacuum was good. It was 10-8. I never allowed operation beyond that point. Vacuum was good. Well, there's very little chance of oxygen. We spot welded the filaments, but these are the sport legs that got fired. Sport legs, they're not actually the filament legs. They are the legs who support which are used to fix the cathode in the assembly. So that could be something else.
Contact resistance.
Contact resistance.
Thermal insulation.
Yeah. Yeah, you're very close. What happened was the alignment was not very good, and the cathode got touched with the head. Sometimes we want to sleep. We rest our head on some support. So this cathode was touching the focusing cathode, and the hot spot created, and that hot spot was not very cooled, because this was at 1000 plus degrees Celsius. This couldn't handle it. Thank you. Excellent. We came to the same conclusion. What about this?
Coating. Metal coating.
Sorry?
Metal coating.
Metal coating.
After the first installation materials.
Yes. Maybe yes.
The vacuums, is that the seal?
This is okay. I'm sorry. I should be more like explaining. This side is air side. This is not in the vacuum. This is in air. It was what is happening in the air. That's why I showed you that we switched to a corrugated insulator, and we do insulation simulations first inside, because after this accident we were very conscious. This was a very a milestone in switching from the geometry to the other geometry. So any other suggestion? What happens is that
Ceramics.
yeah, ceramics. Ceramics are very good insulators, but if you when you take this presentation with you, this ceramic is brazed with the coir, and they were quite near. They were quite near. There was not enough insulation, and the insulation was very weak, and the high voltage field was actually jumping on this thing. If you recall, I partly answered this question here. Tuck, tuck, tuck, tuck, tuck, tuck. Yeah. This was the hot spot. I mean, the spot where the concentration of electric field is much high. We have increased about 20 times the thickness of the ceramic, and again we are using the corrugated what you call fins of the ceramic in order to avoid any possibility of this high voltage to jump to this voltage, to this point, because the flange is at ground. Good. Thank you very much. Homework. This is pure homework. Let me explain it to you. These two guns are very similar, very, very, very similar. But one of them works and the other refuses to work. Forget about the cathode part. The only culprits are hidden somewhere in the neck. Yeah. Spot the difference between the two geometries and guess which assembly will work, and tell me why it will work. You have time period tomorrow.
Vacuum level, because couple of casket, you use other side, another is plastic casket you use.
Okay, let others think also. Yes. I thought it is a homework, difficult homework, but maybe not so difficult for others. But let's, yeah. Okay, since I have a homework problem, so let's not go the details. This is a special topic. I changed my things a little bit, but since many people were asking about the thrusters, electron beams are used in thrusters. They are not the actual part, the active part of that machine. But since they are making a contribution to the thrusters, it can be treated as a part of it, a special topic. And let me discuss very briefly how we use the thruster, the electron guns in thrusters. We have an idea of the thruster. We have a satellite in vacuum. What if you want to change the orbit a little bit? So you just need a little bit of kick because it is already being accelerated, being held in a certain orbit due to the gravity. Huh? So you just need a minor adjustment. That adjustment can be done with sort of a nanonewton thrust. That nanonewton thrust comes from just a blow of air. That blow of air comes, you cannot have air or controlled air in space. That blow of air comes from the xenon plasma or the plasma. Okay. That's it. I just downloaded it from the Wikipedia. This is the plasma which is creating a blow. The blow will act, the force will act on the center of mass, and that center of mass will slightly shift. And if it's the extraterrestrial, what you say?
Geolo.
Geosatellite. Geosatellite. So a little bit of blow can shift the orbit, and then the controls can come into play. What you do exactly is you generate your plasma. Plasma means the highly ionized state of matter. You have positive ions, you have negative electrons slipped off. These positive ions are very heavy because people use xenon. They prefer xenon because it's very heavy. I mean, and it's easy to ionize. It's the last column of the periodic table. Neon, helium, neon, argon. In lab, you work with argon, but eventually you switch to the xenon if it comes to an actual device. Then that positive ions are accelerated because I have to gather the air in my lungs, and then I give them a little bit of acceleration. That acceleration comes from a little potential that is held at few kVs, maybe a little bit, but you cannot let ions to go through go away from this device, because due to potentials they can interact. So you need to neutralize it.
Gravitational potential.
No. The voltage. Electrical potentials. So you need to neutralize it. Only then they will act as balls, soccer balls or something. And the center of mass, the force acting on the center of mass can make the difference. So to neutralize this thing, you need an electron gun which will generate enough electrons to feed these starving ions. Electrons were ripped off this because you need charges to accelerate. You cannot talk to any neutral particle. This was the first lesson we learned this yesterday. If you want to talk to a particle, you have to first create a charge. Only then you will be able to accelerate or decelerate it. So first you create ions. Once you have created them, you accelerate them, and then you neutralize them. So the extra electrons that are needed come from electron source. Okay. So what sort of electron source do you think it should be? It should be a high-end electron gun, or any gun will do the work?
No oxygen base. So you can use any substance, any electron source.
Any electron source, but what should be the strength? Remember, electron gun, if someone comes to me, in fact, one of my students is working on it, Dr. Emosen, and he came to me, yes, of course, and he asked, okay, Kashif bhai, we want to have a gun, so can you, we suggested something, we in fact made one for them as well, but what should be the parameters of those guns? Should be a huge thing? What should be the current? Remember, the client will tell you what is the current that is needed. If you want to feed 50 people, you will make food for 50. You cannot make food for 500. That will be an overkill. You shouldn't be making food for 10 people. So you have to analyze the plasma first. You should know what sort of plasma you have, what is the electron affinity. There's a parameter of plasma. I'm not a plasma guy. So what you do experiments. This is a view graph of a very humble setup in our laboratory. We use it for some other purpose, but the plasma science can be understood here. This is the chamber where here we are using argon to generate some plasma. And this is the plasma which you can see through a window. This is a quartz window, and the crisscross thing is just a what you call mesh. It is installed at the TBAE shield. You know the TBAE shield? It is the boundary of the plasma. roughly speaking. And the moment the plasma comes into contact with this mesh, they get the electrons and get neutralized. So that the plasma is never like able to penetrate from that mesh down. So the plasma stays within a closed vicinity. If I take the light and pass through it from emission spectroscopy, I will see what is going on inside. Light is information. My first experiment, Dr. Shoaib asked me, light a candle and tell me what is going on in it. What's the temperature? What are the species? Everything. That's why perhaps Allah subhanahu wa ta'ala said, related to Nur, the light, the information, the knowledge is light. So what you do, you take your light, pass it through a spectrometer and plot it here. This is a spectrum from one of our 15 years back paper. You have a spectrum from 200 to 1100 nanometers is covering nearly UV and a bit of NIR, nearly infrared region. So what you see are the emission lines. Where those emission lines are coming? Because
Electrons levels.
yeah, electron levels. The electrons jump from higher end to lower orbits, and they emit light. So the density of the state. This was I'm showing this morning. In fact, this helps. The density of the state has the information of number of guests you need to feed. NE, the number of particles that are ionized for certain species. Data is available over the internet. NIST is perhaps maintained by some US agency. We take that data, we have the transition probability for every line, we evaluate the temperatures, and then we get the information about the numbers that you need. So you will define or you will devise an electron gun, which will not be an overkill, which will not be a starvation either, but it will cover this equation. So this equation is actually helping you to model the electron gun to feed every starving species. Once you have fed it, it will be okay. So the plasma will have the enough electron to get neutralized and the thruster should work. So this was the very quick overview of the electron sources that are needed. This is perhaps pretty much the basic of the starting point of the source. It is very different from what you have to do for microwave devices. So the plasma people, they actually do the spectroscopy. Yeah, spectroscopy is a marvel of statistical thermodynamics. The quantum mechanics come into play, and you can play for years maybe. So the electron gun here is basically not the very high-end gun. You just need a few volts, maximum few hundred volts, and then there are just spraying just to cool down your tea or something. And people conventionally use those dispenser cathodes, but those dispenser cathodes that they are preferred are fast ramp-up cathodes. For example, sometimes you have to heat up the system very quickly in order to make last-minute maneuvers. So you need high. That's why this development of dispenser cathodes is very important. Lanthanum hexaboride is a very high-end crystal. I tried to use it, but it needs very high activation temperature. But it generates very high temperatures, so that can be an option as well. So electron guns are very simple as compared to the microwave devices. This is from my side here. There are many books I just give you some examples for vacuum technology. Roth is a good reference for optics of charged particles. Volnik, Herman is excellent choice. Whatever we did today is 80% covered in this book, Theory and Design of Charged Particle Beams. In fact, it has a detailed derivation of the paraxial ray equation. So don't be afraid. If you know the physics, you know statistical mechanics, you can go to the 3rd chapter of this book and do the model. This is a more engineering book which covers the microwave, millimeter wave, vacuum electron devices. Someone has very nicely compiled it, and the guy who has done it has spent his whole work life doing it. After retirement, I guess he wrote this book. It's a very nice account. You must have this thing. And once you are done with this stuff, the beam instrumentation and diagnostics, this is very important if you want to diagnose your beam. For example, the emittance thing is very, very nicely explained in this thing. I owe a great deal of thanks to every one of you, especially my teachers back home, my respected colleagues at LINAC Project Pinstech, my junior colleagues, my students. They all contributed to what I've shown. I was planning to write their names, but I once started I was afraid that I may skip or forget mentioning. So it's a long, exhaustive list. And on top of that, I am very grateful to TÜBİTAK, which provided us with the opportunity to attend this marvelous school. It's a very excellent opportunity to share knowledge, and I myself learned a lot. I thank you very much. Thank you.